good. Um, so at the end of the day, we want to look at the individual effects as well. Okay, so we know that this model is very good, 70.3% of variance. We know that it's likely that we're not getting that due to sampling error. We're confident enough that whatever we're obtaining in terms of explained variance, it's something which is likely to be true. So we're fine as far as our regression model is concerned here. But then we want to know, okay, study time, study motivation, do they both influence ACAD performance significantly? Okay, do they both have a significant effect on ACAD performance? And if yes, which one's the most important one? And furthermore, if we want to predict ACAD performance, can we do that? And what can we expect in terms of prediction? Okay, so three things here. So first of all, we want to see, is there an effect? Okay, is the effect, the individual effect here of a study time on ACAD performance, study motivation on ACAD performance, is it statistically significant? To know about that, the statistical significance of individual effects, we look at the t-value, obviously. Okay, so for the R-square, we make use of the F statistic, F test. Here we're using a series of t-tests. So this is where we want to interpret, all right? So first, we look at study motivation and its effect on ACAD performance. What do we find? We get a t-value of 10.4. Okay, 10.41. And a corresponding p-value of 0.000. So what do we do with that? So we are going to see, is it less than 0.05, 5%? Yes, it is. What do? We reject H node. What's our H node? That study time has no effect on the ACAD performance. That's rejected. And therefore, we can say that we have enough evidence in support of our hypothesis. What's our hypothesis here? So we took this one, doesn't matter. Okay, H2 is supported. The effect of study motivation on ACAD performance is statistically significant. What about study time on ACAD performance? T is equal to 3.451, P is equal to 0.001, which is again less than 0.05. Okay, so what do? We reject H node pareil, and we say that the hypothesis is supported. So that's supported, okay? So that's the first thing we want to do. Good, straightforward. Second thing you want to look at is you want to compare the relative strength of the effect. So to do that, we make use of the standardized coefficient here, beta. Okay, so why do we use the standardized coefficient to compare the relative strength of the effect? C'est que, bien souvent, if we just look at the regression coefficient, it can lead to misinterpretation. Why? Because different variables might be measured using different scale, different units of measurement. For example, here, study motivation is measured on a scale of 1 to 7. Study time measured in terms of hours per week. So it might not really reflect the difference that you have in the effect. So the best thing is to use a standardized coefficient, which is just looking at the unstandardized regression coefficient by standard deviation change. So you just divide by the standard deviation. So basically, that's what we want to use here. And what we can conclude. Now, one thing which you need to bear in mind, if there was any variable here which was non-significant, if one of those was non-significant, then you don't need to carry on with it in step 2 because it is not significant anyway. It does not have any effect. If an effect has been observed, it might be due to sampling error. It's not likely to be true anyway. So if that's the case, then you don't need to compare it with other variables. It's not significant. In our example here, we have both, okay, those two variables. So we have only two variables in a way, two predictors, and both of them have statistically significant effects on our outcome variable performance. And we want to know which one's the most having the strongest effect. And that's straightforward, right? So for study motivation and ACAD performance, we get beta of 0.687. For study time on ACAD performance, beta is equal to 0.228. So obviously, which one's the strongest? The one with the highest value, right? Because it is on standardized, it is standardized, the higher, the stronger it is. Simply so. So here you will conclude that study motivation has the strongest effect on ACAD performance compared to study time. Both have statistically significant effects. Good. Both are explaining substantial amount of variance. I mean, statistically significant amount of variance, at least. I don't want to use the word substantial here, might be misleading. But which one is explaining more variance? Which one accounts for more variance explained? It is study motivation. That's the strongest predictor. Okay, strongest predictor compared to study time. And that's important because if you're doing a study and then of course you want to make recommendations afterwards based on your results, you always want to make recommendations on those predictors which are the most important first, the one having the strongest effect. You want to say, if we have limited resources, we want to act first on those predictors having the strongest effect. All right. So here, if we want to make sure to what we want to take actions and see how we can improve motivation level, look at performance of HSC students. So look at how to motivate them first. So that's the thing. Okay, last step, we look at the regression equation itself, and if we want to make predictions. So in that example here, so what's the equation? Academic performance equal to beta naught plus beta 1 x1, which is, so let me use B instead. Let's use the same notation as SPSS. Okay. B naught plus B1, study motivation plus B2, study time. Okay, of course you have error term. We don't need to consider that. So just replace that. Your constant, the B naught is your constant. But this one is not statistically significant, as you can see here. Okay, so you don't need to even include it in the equation. If it was significant, the constant, you include it in the equation because then it has relevance. It helps to predict the outcome better, so you include it. Here it's not, so whatever we get here, it might be just due to sampling error, so we don't bother about it. We don't want to include that. What about study motivation? So here we look at the unstandardized coefficients. So we have 12.706 SM plus B2, 1.387 ST. Okay. Forget about the error term in the equation. So what does that mean? So basically here, what it means is that for one unit change, in study motivation, SM, academic performance is expected to change by how much? 12.7. Okay. And 12.7 what? Actually, it's in marks, so 12.7 marks. So remember, you have motivation, which was measured on a scale of 1 to 7. So what we're saying here, for example, so if we have, let us say, one student who moves from 4 in terms on the scale of 1 to 7 in terms of motivation to 5, moderate level to quite high to high, we expect that we'll have an increase of 12.7 marks, which is quite a lot. Okay, if we move from 4 to 5, you have an increase of 25.4 marks, which is a lot. Okay, so that's what it means. Same thing here for study time. So for an additional hour of study per week, so you can have 1.3 marks in addition, and for incrementally for each hour. That's what you expect to have. yeah, so that's in terms of equation and prediction, right? And that's it. That's it for the coefficient table, and we're done with interpretation. Of course, you can imagine if you're writing a report, you just make sure you write a nice paragraph and you explain everything well. Okay, but that's the gist of it. Good. Okay. Now, let us see if we have specific conditions now. Okay, and what's important to look at. Let's say now we want to add a control variable to this. Okay. So before we look at assumptions afterwards, let us say we want to include a control variable. So let's look at the same model. So you have study motivation, and then study time. You look at performance. Now, suppose we want to include what is known as a control variable. Let us say gender. I mean, it's just another predictor. You could just have included it as another predictor, but normally, if you know it's only going to act as a control variable, let me do that step by step for you not to get confused, especially those who are not used to it. Let's just forget about the term control variable first. Let's do that step by step. Okay, so let us just say, so we want to just add another variable, okay, and then I will speak about this concept of control variable and how we should deal with it. So just say we want to add gender as another variable, as another predictor. So we have the same predictors, but we want to add another one. We want to add gender. Now, the first thing you need to notice, okay, in terms of how gender is measured, gender will be measured as a dichotomous scale. Well, nowadays, you can have another category over categories. I mean, seriously, in many questionnaires now you have it. But let us just assume that we have just male and female here. Because if we had another category, when it becomes little, you just had another. If you have more than two categories, there's something you just need to treat it differently. I'm going to speak about that afterwards. We just stick to two categories, so it's dichotomous. In that case, you have 0 and 1. It could be any other variable. Like I've just taken gender because I have this variable in my SPSS data set. It could have been anything else. So any variable which is categorical. So we have a variable which is different here because this one was numeric, this one was numeric, this one was numeric, but now we have a categorical variable. Okay, and in that case, we have two categories, 0 and 1. We can include such variables in a regression model. We can include it, but we can only include it as dummy variables. Okay, as dummy variables. So the first thing about a dummy variable is that it is a categorical variable comprising of only two categories and coded as, and what's important, coded as 0 and 1. Where 0 is considered to be the reference group, that's how we call it, a reference group, and 1 is referred to as a test group, or the actual dummy, dummy code. So you have the possibility, okay, to include a categorical variable, therefore, in a linear regression. But to include categorical variables, we need to make sure that they are converted into what is known as dummy variables. So if it is already a categorical variable comprising of only two categories, then it's easy. You just make sure that you code them as 0 and 1. So for example, here it was 1 and 2. You just make sure that in SPSS, you recode it as 0 and 1. Or whatever software you're using. You just make sure that it's coded as 0 and 1. That's the thing. And if otherwise you have more than two categories, which can be the case. So let us say we had another variable. So let's say, for example, you have marital status. Okay, so and you have single, married, divorced, widowed, whatever. Okay, let's say 4 categories here. Yeah. So then we need to dummy code those. If we need dummy code those, the first thing to do is to select a reference group. So let's say this one is going to be a reference group. If we need to dummy code marital status, we're going to have multiple dummies. You can't have only one. If your variable, categorical variable comprises of only 2 categories, then it's okay. You have only one dummy variable because you will have a reference group, reference category, and the other one will be the test group, okay, the dummy coded variable, and that's good. Par contre, if you have a categorical variable which comprises of more than 2 categories, not dichotomous, you have multiple categories, then you will have multiple dummies. So in that case, we're going to have 3 dummies. It's always number of categories minus 1, right? Number of required dummies. So number of required dummies is equal to number of categories minus 1. Alors, par exemple, là, for gender, we have 2 categories minus 1. So that's, you need only one dummy variable. Okay. Where you assign one reference group and the dummy group, test group. Here we'll need to have, therefore, we have 4 categories. How many dummies? We'll need 3 dummies. So first thing you need to do is assign the reference group. And you know you're going to have 3 dummies. So dummy 1 is going to be, let's say, dummy for married. Okay, this category here. You have dummy divorced, and you have dummy widowed. And if you have more than categories, you just add them, doesn't matter. Here only 4, so 3 dummies. So if we have a dummy married, this is going to be 1 and then 0, 0. Here, divorced, so therefore 0, 1, 0. And for this one, I'll call 0, 0, 1. So you will have to create 3 dummy variables. Okay, so that's what you would do if you were dealing with a variable with multiple categories. Right. Again, if you have one which is only dichotomous, then it's only 2. Okay, I hope so far so good. This one I know it gets a little bit time to get used to, so just play around with that. It's not difficult, okay, and you figure out easily what we're doing here. Just take another example. Think of another example of where you have multiple categories and just play around with that, just like I did here, and you get and I'm sure you see that it's not that difficult actually. Good. So let's do that now. We're going to add gender as a categorical variable to our regression model. Okay, so let's go back to our SPSS. Good, and now we have gender, which we want to add. So let's rename it, okay, just to make sure. So we have coded here. So then, okay, it's already in our data set. It's already coded as 0 and 1, so that's okay. So the reference group is female, and the dummy variable is male. Okay, the test group is male. So let's just rename it just to make sure that. So it's going to be dummy, and what's the dummy? Dummy male. Okay, we're comparing male to female. Okay. So we're just going to add this variable. Okay, so let's do that step by step. So we just run the same thing, just I will add this categorical variable here, the dummy variable. Just say okay. Just see how it goes. So as you can see, the our square value has increased a little bit. C'était auparavant 0.703, maintenant c'est 0.715. Okay, so 0.5% variance, it increased a little bit. We added the variable and it explains the model a little bit better. Explain the outcome variable, so a bit better. What do we see in terms of results? We now have dummy mail. So let's see how we interpret that. Let's see how do we interpret that. I think I'm getting sleepy as well. So okay, so what we've just done, we run the same model. We just added one variable. So I'm just going to show you how to interpret that. And yep. So let's do that. Good. Excellent. Okay. Well, we don't need to deal with those again. Ça c'est bon. So those two are still significant. Ça c'est bon. What about the demi-male? First thing we want to look at, is it statistically significant? Yeah, it is. So we have t is equal to minus 2.319, and your p-value is equal to 0.22. What do we do here? Do we reject H note, or do we fail to reject H note? Anyone quickly? Just see what you're still here and you're not sleeping. What do we do?
Fail to reject H note.
Sorry?
We fail to reject H note, right?
You fail to reject, why?
Because the probability is more than 0.005.
Is it more? Sure.
Or no, it's less.
Yeah. I think if yeah, it's a bit
the reverse.
Yeah, it's less, right?
Yeah, it's less.
It's less. Yeah. I knew sometimes it gets a little bit tricky. You see this two here, and you might think, yeah. So, but that's okay. I'm sure if you look at it again, then you. Okay. Well, I wrote that wrongly. So, sorry. I think it's my mistake here. I missed a 0. Okay. So what it is? Less than 0.005%. Okay. If you're not sure about the decimal place, so just convert it in percentage form. Okay, so c'est 2.2% ici, which is so definitely less than 5%. Okay, you can just always do that just as a quick exercise, and just to make sure that you don't miss any kind of 0.0 and there's nothing missing. Okay, so we have a dummy variable here, which is statistically significant. So in terms of relative importance, it's less than the other one, but it's still quite large, and it is statistically significant, so it matters. But how do we interpret that? That's the important thing. Obviously, you can't interpret it the same way. So let's write the regression equation. Actually, we definitely can't interpret it the same way. Okay. So let's not write the constant. The constant is still not significant. X minus. Okay, demi-male. So you can't interpret it the same way. You cannot say here that for a 1 unit change in gender, it would not make any sense, isn't it? It would not make any sense to say 1 unit change in gender. That doesn't make sense. What we're saying here is that compared to female, which is your reference category, so that's what you can do. Your reference, compared to the reference category female, academic performance. So if the student is actually male, if the respondent is male, so is a dummy one, what do we expect with ACAD performance is going to decrease by minus 5.8 5.8-ish marks, about 5.8 marks. That's what you expect if you have one here instead of 0. So what it means is that actually gender generally has a significant effect on ACAD performance. That's a point to note. And more specifically, male students are associated with a lower level of ACAD performance. So if a student is male, so if you have a given amount of study motivation, let's say that was 4, and this one study time was 10, so you can estimate a certain ACAD performance. Okay, what would be your estimated number of marks here? Okay, just approximately 55, more than 65. If the student is a male, you need to discount minus 5. Okay, so it's going to be associated with a lower level of academic performance, and more specifically, around 6 marks less. So any male student, if you have to make a prediction, you will just discount 6 marks. Okay, that's what it is, and the effect is statistically significant. You see, so that's something very useful to add. Okay, dummy variables in a regression equation. So, well, it does help to make better predictions, isn't it? And that's something very useful which you need to take into account. Okay, now what to know, okay, how to deal with dummy variables and how to interpret them. So I just want to add here, and I think we'll be done with it more or less. When we add dummy variables like that, normally the way we do that, so same predictors again. Instead of considering it like any other predictor, even visually, we just make sure that we present it another way. So for example, here, gender will be considered to be what we call it, referred to as a control variable. Now, obviously, in any particular model, you can have more than one control variable, like just you might be having more than 2 independent variables. You might have more than one control variable. So in our case here, we have one control variable, which is gender. Okay. Now, it's just not just about representing it differently. It's also about how you do the analysis and carry out the regression analysis. But just one additional step, which usually you want to actually do here. So when we do the regression again, and we consider gender as a control variable, what we simply want to do is do it by step. So normally what we'll want to do is first, so add the control variable or variables, if you have many, doesn't matter, when you add all the control variables here. And then you click next here. You click on next. You see the button next here? Click on next. So what we're doing actually, we refer to that as a hierarchical variable. It's not necessary that you have control variables which are measured on a categorical scale. Those could have been numeric as well. It happens. You might have control variables which are numeric, especially if you're doing research on and you're testing a model which has already been tested previously, and now you are adding new variables. So then those variables which were already included in previous models, you might consider them to be control variables, because those are not like of much interest to your research. You just include them because they have been found to be important in previous studies, and therefore you say, okay, they will account for a certain amount of variance. So you want to have your specification of a model right. You don't want to omit important variables, and that's something important actually when estimating regression equation. But then you just include them as control variables. Then in that case, a good practice would be to just do hierarchical regression. So in that let's say regression model 1, you include all those variables which are considered to be control variables. It could be categorical or non-categorical. In our example here, we just have one just to keep it simple, but it could be many, it could be numeric, non-numeric. Then the next step, you add the main variables. So you next, and here we add study time and study motivation, which are our two variables of interest, and that's what we want to focus on. And we click on OK. We get the same results here, and you see the result could be a little bit different. In fact, the only difference that we'll have here is we have estimated the models in two different steps. So we have actually estimated two models. One model without the predictors, study time and study motivation. So the model only with the control variable, in that case, gender. That's model 1. And then we have model 2, where we have included all three variables. So you will see everywhere now in model summary table, model 1, model 2. Your ANOVA table, model 1, model 2, and your coefficients table, model 1, model 2. Now you can clearly see in the coefficient table, so model 1, you have only dummy male, and then so your control variable. Then model 2, you have those three variables, all the variables, right? But the results basically same thing here. So we have our square, but for the two models separately, the ANOVA for two models separately, and then we have the coefficients table here. Okay. When you do that, there's one small additional step which you want to do. So you go on statistics and you click on R squared change. And you click on R squared change. And what this is going to give you here, you will see it gives you some supplementary information, change statistics. What it's telling you is the second model. And if you had a third one, you could even do a third one, hierarchical in terms of 3, 4 levels. It doesn't matter. In our example here, we have 2, and normally you stick to 2. So what's telling us is there this change in R-square value, moving from 0.299, so it was only 2.99% of variance explained, moving to 71.5%, is this change in R-square value the additional explained variance when you add the other variables, in our case, study time and study motivation, is this change statistically significant? And we want it to be statistically significant, right? In our case, it's going to be clearly statistically significant because we have only added one control variable, and that to a generic kind of general one gender. So we do expect it's going to be statistically significant. It can happen, but it's not. Okay, when you have a problem, it means that was not a problem as such, but like what it would mean is that whatever variable that you have considered for your research, which is really additional variables not considered previously, we do not really substantially contribute to explaining variance in the model. It must still be interesting, as we say. It's not like everything is bad because of that, but it will mean that your model is not really, those variables are not really adding anything in terms of explaining your outcome variable. That's what it means. Okay, good. Okay, so those are just additional stuff. Otherwise, whatever we said previously still hold. Okay, so there's also a few additional stuff. So we can add dummy variables. If you want to add categorical variables in your regression model, that's one. And second, you want to do it in steps, so do it in a hierarchical manner when you want to include control variables, which is something very important when estimating a regression model. OK. So hopefully we're fine. OK. Alors, c'est pas vraiment compliqué, mais c'est juste adding some few features to it, depending on the research you're doing. And yeah, normally those are things that you do include in a regression model. Some control variables and some of those variables will be in categorical form. So those are things you need to know. Good. Okay, time is running. Time is running by. It's already 8:10 now. Okay. Let us speed up. We still have something to complete. We need to look at the assumptions. Okay, we still need to look at the assumptions. So I'm just going to wrap up on those. Yes, Anusha is speaking about culinarity. That's exactly what I need to speak about. Okay, so the assumptions. So let me touch on that. Okay, let us look at the assumptions and then we're good for regression. Okay, but I really need to complete that. So just take a breath. Okay, 1 minute, and then we complete with regression. It's a good thing if we can just, I know it's hard after a full day work. Trust me, I've also had a very hectic day today, a lot of administrative work to deal with all day. So I'm also a little bit tired, but yeah, it's good that we finish with that. And so just a last effort that I need from you, and just to focus on that, and then we're done with that. So just 1 minute, breathe a little bit so that you can focus. Okay, assumptions. Is the assumptions, and then look at what we refer to as robustness checks. Okay, in the context of a multiple linear regression. So we have a few assumptions which pertain to the residuals. Remember what we mean by residuals? What is the difference between predicted values and actual values? Right? This is known as residuals. So we have a number of assumptions related to that. First, we need to look at the normality of the residuals. Right, you have a distribution of residuals to be precise. Second thing, you want to look at independence of residuals. We'll see often we refer to that as the fact that there's no autocorrelation between the residuals, no autocorrelations. And third, we have the assumption of sedasticity. Right. So those are the three assumptions that pertain to the residuals. Then we also have a couple of assumptions relating to the variables themselves. So you have the assumption of multicollinearity. Now, well, the assumption actually is no multicollinearity. There should be no multicollinearity. And you have the assumption of linearity, right? So we're looking at multiple linear regression. So we expect to have linear relationships between the different variables. Good. So those are the main assumptions, okay, that need to be tested. So let us see now, how do we test for those? So we're going to see what needs to be done. And so for normality, so we're going to refer to the histogram, okay. And we're also going to look at the PP plot. Okay, so we're going to just do a visual inspection for normality. Okay, so that's what we'll do. For independence of residuals, we have a specific statistic which we're going to refer to use. So that's a Durbin-Watson statistic. Okay. And then for homoscedasticity, we're going to look at, again, a visual inspection. Visual inspection of a scatter plot, basically. And it's a scatter plot looking at the standardized residual values against the standardized predicted values. Okay, I mean, you're going to see what we really mean by that. Multicollinearity, we're just going to look at the variance inflator factor. So we refer to as VIF. Okay, that's what we're going to refer to. And for linearity, we can just look at a scatter plot between each pair of variables. Okay, so between study time and ACAD performance, between study motivation and ACAD performance in our case. So let us just do that, okay? Each of us on SPSS. So what are different assumptions? You need to cross-check those, and then you can say that your regression result can be trusted. So your estimates should be good and reflect the truth. Okay, so let's look at that. Sorry for dog box. Okay, so for the assumptions, we're going to analyze, okay, regression, linear again. So same model, which we were testing previously. But now we're going to choose a number of options. So first we go on statistics. And here we also want to select collinearity diagnostics. Okay. We also want to select Durbin-Watson. By the way, it's always interesting to have a confidence interval as well. Always, just check that. But something else, okay, just to have a confidence interval. So, but what you want for the assumptions, so collinearity diagnostics, what you need to check, and Durbin-Watson. Then we go on plots. And here, that's the assumption of homoscedasticity. So we want to plot a scatter plot between the Z predictor values and the Z residual values. What we also want is a histogram and humanity probability plot. So continue. And we're good. Okay, so we have now all the required different robustness checks, okay, to check over assumptions. Let's proceed step by step. You will see from the model summary table, you have Debin-Watson here. Okay, so that's one of those robustness checks. So the Debin-Watson value here is 2.086. So what do we make out of it? So you see Debin-Watson. So the Debin-Watson statistic here, what we have. Right. You want it to be between the Debin-Watson, you want it to be between 1 and 3 to say that it is good. If it is outside the range of 1 and 3, then you have concern. You have residual values which are not independent of each other. And that's something important, okay? Now, just as an aside, to estimate a regression coefficient, we make use of the OLS technique, ordinary least squares, okay? And it's very important that we have residuals which are independent. Otherwise, the estimate might not be correct. Just give me 1 minute, please. Hey, Zion! Shh. Hey. Yeah, sorry. Okay, so we want to be what's between 1 and 3. So that's one thing. So we had the value of 2 there, okay, 2 something, okay, around 2. So we're good with regards to independence of residuals. Next, if we move on here, you will see in this table, coefficients table, now we have what is known as the collinearity statistics. And we have those VIF scores here. And those are the values you want to look at here, okay, VIF. So 1.4, 1.8, 1.5. So the smallest 1.43, the highest 1.8. Okay, so just take note of that. Smallest VIF value that we have 1.4, highest 1.8. For the VIF values, we normally want it to be between, so VIF, you want your VIF values to be, actually, you don't have a lower value here. You want it to be less than 5, less than 5, to say that it is good, to say that you don't have multicollinearity. Now, what is multicollinearity? You see, you test a model like that, you expect that you have some correlation between your independent variables, but it is expected that you will have some correlation between your independent variables. It is expected. For example, here, a study motivation, study time. You can easily imagine that students who are more motivated will tend to study more. So you expect to have correlation between those. But you don't want to have very, very high correlation. You don't want to have a correlation of 0.9. Even 0.8 will be quite high. So you don't want those to be very, very high. Okay, so that's what we're testing for here. But we don't have too high correlation between our independent variables, because again, if that's the case, then our estimators becomes biased and we can't rely on those. So here it is between 1.4 and 1.8. So it's well below 5. So we're good as far as multicollinearity is concerned. So there is no multicollinearity. There's no high collinearity between our independent variables. So we're fine with regards to that. Okay, so that's the next assumption. Then we move on, and now we have our graphs, and we can do our visual inspection. First, we look at the normality. So here we're looking at the distribution of the residuals and see whether more or less they follow a normal distribution. And we can see here there is some skewness happening. So just looking at the histogram, you can see it's quite skewed to the left, and it's confirmed there looking at the PP plot. Okay. So normally, whenever you have an assumption which is not met, we have remedies for that. Okay, it's not the end of the world. It's not that you just need to stop anywhere. There's nothing else you can do. No, we have remedies. And for example, if you have the assumption of normality which is not met, then you can do a bootstrapping. You can use a bootstrapping procedure. That's one possibility. Another possibility is to do a data transformation. For example, you take the logarithm, the log form of each of the variables. In SPSS, you can easily do that. You go and transform, compute variable. You take the variable and you just convert it into a log form or whatever other forms you want. So depending on the nature of the violation of your assumption, so skewness or high kurtosis, whatever it is, there are different transformations which are recommended. So you can play around with it and see what works best. Okay, you can take the log, you can take square root, you can square it, you can take a cube. There are different things that can be done. Would you take the inverse form of your variable? Okay, I will be sending you some additional notes on that. Okay, so in regards to what are the potential remedies when you have assumptions which are not met. For example, here for a normality, yeah, there seems to be some issue. How do you interpret the PP plot normally? So you will expect that all the dots here are along the line if the distribution was perfectly normally was following a normal distribution perfectly. So it's not the case here. So you will see a number of bumps here. It's not severe because otherwise it's already severe. You can just Google that and you find severe cases, MPP plot, how it looks like. It was going to be much more like deviated from the line. It's not a severe departure, but yeah, you have quite cause for concern and you might want to just do a transformation here. A log transformation might do, for example, here. So that's for normality. Okay, so we check it. It's not severe, okay, but following a visual inspection, you might want to take a remedy, either do a bootstrapping or do data transformation. Okay, well, nothing much to add here. For this one, you want it to be according to the line. This one, you look at the normal distribution and see whether it follows a normal distribution. Okay, that should be, you see what I mean? Okay, normal distribution. Right. So visual inspection for histogram, following normal distribution, PP plot, dots along the line. So let us say we check that, and well, for us it is cause for concern. We can do data transformation. What about homoscedasticity? So for homoscedasticity, we look at this one. Okay, and what we want to see here is that you have a randomly scattered scatter plot. So you want to see the dots here randomly scattered. You don't want to see any pattern, specific pattern emerging. So let me just show you how that would look like here. So if you have hetero scedasticity, that's what you would kind of expect here. Okay, so if you have data which is heteroscedastic, that's the kind of pattern that you would expect to have here. Okay, so small amount of variance at the start and a big amount of variance. Okay, that's interesting. So you have here, that's perfectly homoscedastic, and that's where you have heteroscedasticity. Do we find that here? Not really. Okay, it's almost randomly scattered, isn't it? You don't have really a pattern here which narrows down. So we're pretty fine with that. Again, if there was issues, we have remedies. Okay, depending on the nature of the violation of the assumption. Okay, you can transform the data. So I mean, the main remedy is data transformation. That's what you want to do if you have any assumption which is violated here. Okay, then. So we're good. We're good. I think we're done. So that's good. So that visual inspection. And well, for linearity, this one you just scatter plot with that, and you just see if you have roughly a linear relationship. You don't see any pattern in terms of curve linear. So this one, I think you're good with that. You know how to do that. Okay, so I think we're done. Okay, so that's assumptions, robustness checks. I'm going to send you some notes, further notes on that, everyone, and hopefully that's okay. Well, it's already 8:30. Sorry for having kept you so long. So I think we made it. We're good. One thing I think which we can do, we can send you. I can send you maybe a question to work on a post exam paper, and then if you have specific questions on that, you might just let me know, and yeah, I'll try to answer that. C'est bon. So we're done with our regression analysis. So anything which, yeah, so we're good. Any questions you might have, specific questions? Definitely. Yep, you're feeling sleepy. You already asleep, everyone. I see many of you have left, so you are sleeping. I mean, but I can understand that. No worries.